Hi everybody, this is section 9.5, probably the most involved section that we're going to hit in this chapter. And the hardest part about this chapter is figuring out how to write your final answer as far as MyMathLab is going, with what they expect. So there might be a little bit of playing around to see you know, if we get a final answer and it doesn't really like that form, then I'll show you how to change the form and stuff. And it seems like every problem is different, so there's going to be a little bit of experimenting going on here with MyMathLab. So we're continuing our radicals. We're going to see how to work with them and, most importantly, simplify them. All right, there's a lot to radicals, as you've probably already seen and figured out. So, all right, so remember what we have. We have our among other things, we have our product and quotient rules. So we can't forget those. We're going to use those quite heavily here. The product rule was this one, and the quotient rule was this one. So we're going to use those. Okay, we're going to combine radicals or split them. And then we have to remember what are the four things that we need to have in order to have a radical be considered to be simplified. So the first thing was no perfect nth root, right, underneath the radical. So here we can't have a perfect square because we're dealing in squares here, but we're going to go into thirds and fourths here pretty quick. So just a perfect nth power, or perfect nth root underneath the radical. No radical in denominator, which we're going to run into that we can't get rid of the ways that we've already learned, so we're going to have to learn a new way to do that. One radical. When we're multiplying and dividing. Now addition subtraction is different. As you can see up here, we've got we're going to have subtraction. So this is different. So only one radical when we're taking a, well, let's get rid of that one because that one's got so many exceptions to it that we're going to see in this section. Let's just take that one out of there. Most of the time when we're multiplying and dividing, we can't leave something like this. We have to bring it together. And then the outside pieces have to be fully reduced. Let's just say reduced, simplified, whatever we want to say. Okay, so that's when we consider a radical to be completely finished. And then MyMathLab's gonna, go from back and forth between, does it want it as one fraction, does it want it as two fractions, that kind of stuff. So we'll just play around with it. So let's start out by distributing. That one's using the distribution law. Okay, that's no different really than this, right? Is equal to AB plus AC. This is the distribution law, so this is what we're going to be doing here. Just multiply each piece by the square root of 2. Okay, so really fairly simple stuff to begin with. So I'm not going to do a whole lot of these. Okay, so each piece gets multiplied by the square root of 2. And then always the hard part is simplifying. When do you stop? Obviously not here. We'll bring these two together here under one radical. Now this back piece, you can't do much with that, right? But what's inside of a 32? Well, we should look at our perfect squares again, and maybe I'll write these down. I'm just grabbing them here. Maybe we'll write these down as we need to use them. So my perfect squares were what? 1, 4, 9, 16, 25, 36. I'm getting better at this. 49, 64, 81, 100, ... Okay, so these are my list of perfect squares. So, you have to look to see what's inside of all of this. Now, what is 2 times 32? Well, that's 64, right? We can multiply that. Okay, so 64 is a perfect square within itself, right? It's 8 times 8. So we can say that this is equivalent to 8 minus 3 roots of 2. Okay? Now, checking. Well, I'm not going to do a ton of checking just because it's very time consuming. But I will check, you know, a certain few of these. What I'm doing here is I'm trying to get some sort of a decimal equivalency on the original, and then a decimal equivalency on my answer, and see if they match or not. And they do. Now that's not going to tell you if you have the right answer. It's going to tell you that you have not changed the value. But, you know, if you would stop up in here, you would also get that same value, but it's not the right answer. So it gives you an idea that that you haven't changed the value, which is half of it. The other half is, you know, when have you stopped simplifying? How far have you gone? Okay. One of the biggest mistakes I see here is this. Okay, you can't do that. All right. Think of this as this. Would you ever say that this is 5x? Well, no, you'd never do that. So don't do that here either. This is not reducible. Okay? So let's just start playing around with this stuff and see what my math lab wants. Like I said, we might have to do some fudging around in here because these are difficult to get into my math lab. All right, foiling. Does anything change with foiling on radicals? No, it really doesn't, right? Now we're just going to take the first two, the last two, these two, and those. Okay, so I'm going to let you go on that one. I'm not going to do all of these. It's going to be way too long if I do all of these. There's 20 problems in here. And, you know, just use all your rules of simplification. All right, maybe we'll do this one because it's just slightly different, not too different. Remember, whenever we have the square here, that means that we have two of them. So this is a foiling problem. Okay, so we're going to do the first terms first. So you're going to multiply 2 times 2 for a 4. Then you're going to want to multiply these two, okay? And let's just do a little bit of work up in here. Okay, we can use the product rule, right? The square root of a square is itself. So this is the natural progression to get to there. So this is just a 4x, right? Now I'm going to do the outside piece. I've got 2 times 3 for a positive 6 square roots of x. Got to have that on the back. And then my inside piece is going to be 6 roots of x. And then my last piece is a 9. Now these can be combined because, why? Because the radicands and the indexes are the same. So really I have 12 roots of x plus 9. Okay? 4x plus 12 roots of x plus 9. Should we check that one? I think we might have to check a lot of these just because I don't want to get, you know, stuck in that, well, yeah, it's similar to what it wants, but not really what it wants. And then you guys are going to be stuck. Okay, so this is no different. Okay, we're going to foil, 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 right? Simplify, simplify, simplify. This time we've got cube roots, which is fine. You know, see what 14 times 14 is. What is 14 times 14? Well, it's 196. Now you've got to see whether or not there's a perfect cube within 196. Okay? You have to start hunting around for one. You know, see if it's divisible by, for instance, 64. Nope. 196 is divisible by 27. So when you have a final answer, nope. So when you have a final answer of, you know, radical 196 on the back end, you're going to have to make sure that there isn't a perfect cube still sitting within that. Because remember, one of our rules here is that you can't have a perfect nth root underneath the radical sign. Okay? So we'll see that. I'm not going to do that one for you, but maybe hang on. Was that one of those? No, I think that one's fine. I think you'll be fine on that. Okay. So now one of our rules that we have here is that there's no radical sign in the denominator. Okay. This one has one. And in the past, this would have been like 9 or 16, and then it just comes right out, right? But the square root of 11 is, what do you do with that? There's nothing you can't, that's prime. I can't break that down in any way. But I can't leave it because one of my rules says I can't have a square root in a denominator or any radical sign in a denominator. So I've got to get rid of it. Well, how do I get rid of it? Well, I get rid of it by rationalizing. Okay? So if I have this, I can always multiply this by 1, right? I can multiply anything times 1 and I don't change the value. But 1 can come in many forms, right? Right? As long as it's just the same thing divided here, these are all forms of 1. So I don't change the value. So what I'm going to do is I'm going to multiply this by a form of 1, but it's going to be a very special form of 1 that's going to get me to where I need to be. And that would be to double these up. I've got an index of 2, right? So I want 2 of everything. I want pairs. Well, I have to have it as a form of 1, so I've got to do the top as well. So what does that do for me? Well, now I'm going to multiply because I've got 2 fractions. I've got that on the top. This is the square root of 11 squared, right? I've got 2 of these. So the top is this, right? And the bottom comes out, the square root of a square is itself. These are all of a sudden looking like tally marks to me. And then we would simplify the outside pieces, so we've got the square root of 11. Well, let's see if that's true. Let's see if that's equivalent. So we're going to see if 11 divided by the square root of 11 is the same as the square root of 11. I hope I'm showing you guys, and it is, I hope I'm showing you guys to check your work in a test situation, and then, you know, carry that through to all math classes that you take. I mean, if you're going on to college algebra, which I'm assuming you are since this is college algebra prep, you know, every time that you get in a test situation, check your answers where you can. You know, take that full hour or whatever, you know, length of time you've been given to take a test and check your work. One of the things I see, I mean, I've been a teacher forever, and what I see is, you know, a lot of people think that taking a test is a race. You know, I got to get done, I got to get done. It's like, no, I'm always, when I was in school, I always was the last one to turn in my test because I wanted to check and recheck and triple check. I just used the entire time. I drove myself crazy sometimes because it's like, okay, how many times can I check this? But you get rid of those silly mistakes, you know, and if you make nice detailed work like this, you can go back and go, well, if this didn't match, I did something wrong. So now I can go back and I can figure out what it is that I did wrong and adjust it. Okay, so we're going to really be careful about checking our answers on a test situation, but I think you guys have been doing that because your test scores show it. You're going to get some really good test scores. All right, so let's keep going here. Let's rationalize. Okay, so the problem here is, number one, I have 2 radical signs. That's what I'm talking about when it's just one fraction like this. Okay, not when there's pluses and minuses and things like that. That's the exception to the rule. So whenever it's just like one thing, you can't have more than one radical sign, and I certainly can't have one in the bottom. Okay? So again, I'm going to want to multiply by that special form of 1. I've got 1 square root of 7, so I want 2 of them, top and bottom. Okay? Now this is always the square root of 7 squared, which is 7. That's just standard. You see how that these two wipe each other out, just like these two become 11? That's always the way it's going to be. And here I have 35, and I have 3 times 7. I can combine these with, let me find it, this, right? My product rule. Good. So I have 35 times the square root of 21 over 7. Now let's look at my rules. My rules say I can only have one radical sign, check. Can't have it in the denominator, check. And then it says I can't have a perfect square underneath this. Well, 21 does not have a perfect square. I mean, if it was 20, I'd have to pull the 4 out, as an example. And then it says my outside pieces need to be reduced. Well, that's the only thing that I can keep going with, okay? So 35 divided by 7, 35 sevenths, right there, there's my outside pieces, is 5. 5 roots of 21. Okay? Now you're going to want to throw that in your calculator, get a decimal, throw that in your calculator and get a decimal, and they've got to match. Okay? On your homework, you can do that. You can let my math lab check it for you. Okay, this is the same thing. You know, they're going to be slightly different, but, you know, basically the same. Now on these, I want you to, it's going to be easier. Okay, it's going to be easier if you, instead of multiplying by the square root of p cubed, it'll be easier to, whenever you can, reduce down your radicals before you start rationalizing. Okay? It's just one step easier than if you wouldn't, but you can do it either way. But this right here is p squared times p, right? And then I can split, and I can pull out the p. That sounds terrible. Pull out the p. Okay? Now this p can stay there. It's not underneath the radical sign anymore. So I just want to get rid of this radical sign right there. So now I'm going to square root of p, right? So I can bring all that together as 3p squared. And this is, you've got the 1p, that's this one, and then these two together make another p. And then we have 9. I can split this one. You know, skip steps where you need to, right? I mean, and then this is p and p squared. Now here we've got an outside piece that can be reduced. 9 roots of 3 over p. P divided by p squared is p. All right. Let's see if it likes that. Do I have to do my, can I do it this way? Ooh, I don't know if it's going to like that. Did it drop that down? Let's see. Oh, it did. It took it. All right, or you could do, you know, hit the fraction key first and then fill in the top and then the bottom. My math lab is so picky. It's crazy. All right, I'm going to leave you alone on that one. Okay, so here, again, I think it's going to be easier if you reduce first. I need a new screen. I'm not saying that it has to be done that way, but I just found, not always, but in general, whenever I say, you know, do this because it's easier, it's not, you know, 100% of the time. It's in general. It's like when we factor. In general, if you take out a GCF first and then factor, it's easier, but not always. Okay, so when I say stuff like that, it's never a for sure thing. So I usually, just because usually it is, I'm gonna reduce first. Okay, so the first thing that I'm going to do is I'm going to split this with my quotient rule. I don't want those together. Okay, so now I've got, you know, square root here. So I'm going to start pulling out perfect squares if I can. The biggest perfect square within a 50 is 25. And 9 is not divisible by 2, but 8 is. So I'm going to have 8 and 1 left over. And 7 is not divisible by 2, but 6 is. And I would have 1 left over. Okay? Now I can separate my perfect pieces, these two, put them here, x to the 8th. And I'm going to put my non-perfect, my 2x, over here. And do the same thing down here. This one's perfect, y to the 6th, and then I've got that y left over. Okay? So this comes out as a 25 x to the 4th. Remember, it's 8 divided by 2, whatever the index is here. So I've got 5 x to the 4th times 2x. This comes out as what? A y cubed. We've got 6 divided by 2. We're also looking for groups of 2. I can get 3 groups of 2 out of there. And then I've got that. Okay, so far what I've done is I've reduced my perfect squares out from underneath there. So that was one thing that I needed to do. I have a double radical here. That's not allowed, and certainly not in the denominator. So I want to just leave this there. I don't want to mess with that. That one's fine. It's this thing that's got to get rid of. So again, I'm going to want to double them up because I'm in square roots. Now when I'm in triple them up, I'll be in cube roots. Okay? These two can be combined under 1 because of my product rule in reverse. So I'm going to throw them all underneath 1. And this is y cubed. And y, the square root of y times the square root of y is a y, correct? And then we have, boy oh boy, y to the 4th. Okay, so I got rid of my double radical. I got rid of the radical in the denominator. Now I've just got to, and I already reduced everything down. So I'm just going to take a quick peek to make sure that everything underneath here is reduced still, because I did throw something underneath there. And then I'm going to look to see if I can't reduce anything here, and I think I'm done. So, one of the things that I'm going to do here, just because it's quicker, is I'm just going to put in a 1, and then I'm going to check my answer this way, okay, because it's faster and I've got 20 problems to do here. So it looks good, right? Now they have it as 1 fraction times this, which is they've pulled this off to the side. These are identical. If MyMathLab doesn't like it like this, then just change it to that. Okay? All right. So yeah, I'm going to get a lot of these wrong here. Okay. So now we have the cube root. Okay? Let's try one of these. 135 over 4. First thing I'm going to want to do is I want to split it using my quotient rule. Okay. Now, this is a trick here that I'm going to show you. Could I multiply both top and bottom by the, the 2 cube roots of 4s? Well, yeah, I could. But again, I'm always looking for the lowest thing that I can turn it into. So look at what I have here. 4, isn't that 2 squared? How many 2's do I have underneath there? I've got 2 of them, right? I need how many? 3. Okay, so I only need 1 more. Now I've got 3 of them, top and bottom. I'll show you. Maybe I'll do it with the 4. I'll do it both ways just so that we can see it's the same. Okay, now what do I have? I have the cube root of 135 times the cube root of 2 over here. I can combine these, right? So I've got the cube root of 2 cubed. I'm trying to get these two things to match, because when they match, it's just the 2. Okay, so I just have a 2 underneath. See how that works? Now I'm going to combine with my product rule, 135 times 2. Okay, so I'm going to take 135 times 2 for 270. Okay, so I did get rid of my double radical. I did get rid of it in the denominator, but I'm pretty sure I've got something going on here. right? I mean, again, we can't have our perfect cube sitting underneath there as a final answer, okay? So I can see right away that there's a 27 in there. That one's pretty easy, 27 times 10. Remember, 27 is a perfect cube, right? Then we can split. So I think the hardest part about these is knowing, you know, am I done? The cube root of 27 is 3. This is pretty much set, and then I've got the 2 underneath there. Okay, so I've got, this is my final answer. I can't reduce a 3/2. Now, that was one way of going about it. That was making this into a 2 squared. Now, what if I didn't do that? Well, should we do it the other way? Okay, I'm going to split it first so I don't have to, I don't want to redo that. Okay. Okay, so we're going to rationalize right from the get-go. I've got 1, 4. How many more do I need? 2. Okay. Just makes all the numbers bigger. It's harder to work with. I still have 3 4s underneath there, right? Because I had 1, I added 2. This can be 135 times 16. See how these are going to get huge? A lot harder to work with. This is a 4. And this is a cube root of, I don't know, 135. See, I don't like doing this because then I'm working with numbers that I don't really know what's going on in there. Okay? Well, this one's pretty easy, but a lot of times they're not. Okay? So now I have to say, well, I've got, you know, a perfect cube is 216. Well, that's pretty obvious that it's 216 times 10, right? The cube root of 216 is 6. So that can come out. So we've got 6 roots of 10 over 4. Down too low here. And now I have to reduce my outside pieces. 3 roots of 10 over 2. 6/4 is the same as 3/2. So either way, we can get there. I just don't like working with big numbers like this. Because usually, I mean, this one's easy because I can see it. Like I could see that one. But sometimes you get these numbers that you're just like, well, what's in there? I have no idea. So the smaller you keep them, the better off you're going to be. Okay, so in any case, we've got 3 square roots of 10. And we're dividing that by 2. All right. Isn't that what I have here? Oh, it's cube roots of 10. Somehow. Start all over again. Okay, let's do this. Did I put square root down here? I did. I dropped my cube. Do you guys do that too? Okay, so we have 3 cube roots of 10. So we have a cube root of 10 divided by 2. Now this time I did my fraction first, and then I started filling in. Okay? So if you make a mistake like that on a test, I'll give you a half a point, because it's so easy to forget that you're working in cube roots on your final answer. I mean, if you can get all these numbers correct, if you can get that one and that one and that one, obviously you've been working in cube roots. But if you just forget at the very end to put that in, or you put in an X instead of a Y, or something like, you know, something small like that, just let me know through email, and I will, I can fix it pretty quickly. All right? I'm not that mean. All right, so you can do it again with the fourth root now, right? I have 1u and 1v. How many do I need underneath there? I need groups of 4. So I'm going to have to multiply it by the fourth root of u cubed v cubed, top and bottom. Okay? So make sure that that's what you're doing there. I'm not going to do all of these. I'll never... Wow, the 7th root. Huh. Should we try that one? Just, not that it's hard, it just looks fun. I don't know. I'm going to split it from the get-go. It's a good thing we have low numbers here so we don't have to mess with it. All right, so I have how many z's? I've got 1. How many do I need? I need groups of 7. So what do I need? 6 more. Right? Top and bottom. 7z6. These can be combined with the product rule. 2y z to the 6th. And this would be just 1z. Why? Because we can combine them with the product rule. Right? Z to the 7th. When these two things match, it comes off. Okay? Should we check it? Should we check it the lazy way? I love checking it the lazy way. Where's my answer? 7th root, 2y, z to the 6th over z. Perfect. Makes it look like we're not doing a whole lot here. Okay, so here we are kind of switching gears again. I have addition with a radical. Now that's different, right? So far, I mean, look at what we've been dealing with here. We've been dealing with just a solid piece with no addition, subtraction in there. Look at all these, right? Even that one. Okay, now all of a sudden I've got a plus in here. Okay, so what we're going to do is we're going to multiply by the conjugate. Well, what's a conjugate? Conjugate. Well, if I have 1 plus the square root of 2, the conjugate is 1 minus the square root of 2. Okay, what I'm doing is I'm keeping these two pieces the same, and I'm changing my sign in between. So if my expression is 3 minus the square root of 7, my conjugate is 3 plus the square root of 7. Okay, so that's a conjugate. We're going to look at those with our complex conjugates as well, okay, when we get into our complex number system. Why do we have conjugates? Well, you'll see when we work one of these what it does for us. All right, so I can't leave this as a final answer because I've got that radical in the denominator. So that's the issue, right? There is no other issue because I don't have a perfect square underneath there and I can't reduce anything and you know that kind of stuff. But I do have that radical in the denominator. So what I'm going to do is I'm going to multiply top and bottom by that special form of 1 again, but I'm going to multiply by the conjugate. I have 5 plus the square root of 3, so I'm going to multiply by 5 minus the square root of 3. Top and bottom, so it's just a form of 1. Okay? Now I'm going to have to start reducing this. I've turned, you know, now I've got a mess here, but it can be reduced. So on the top, I'm distributing, multiplying. So 7 times 5 is 35. And then 7 times a negative root 3 is minus 7 root 3. Underneath here, we're foiling. Okay, so we've got 25. Here we've got a negative 5 root 3. Here we have a positive 5 root 3. What did I just do? I wiped out my square root, didn't I? Minus 5 roots of 3 and plus 5 square roots of 3 are gone. That's what always happens when you multiply a binomial times a binomial and they're opposite signs. Those middle terms always drop. That's my goal. Okay, I don't want the radicals in the bottom. Now my last term, I've got a positive times a negative, so I'm going to have a negative. I've got the square root of 3 times the square root of 3, right? Is the square root of 9, which is 3. Do you see how I wiped my radicals out of the bottom? It's because when you multiply binomial times binomial in that way, they go away. All right, so now I have 35 minus 7 roots of 3. These two I can combine for 22. Now here's where I don't know how it's going to want it. This is one fraction, and I don't know if it wants it split or not. So let's see. I'm going to check it and see what it wants so that you guys know how to put your answers in there. Wow. it wants the 7 factored out of there. There's probably, oh, I'd say a good 5 different ways that I could write this, and they're all the same and they're all correct. So, yeah. See how there's a GCF of a 7 in here? So it wanted that. I'm not sure. You guys can kind of play around with it and see what it wants. So if I take the GCF out of there, that leaves a 5 minus root 3 over 22. I don't know why this is more preferable to that. That's one of the issues with MyMathLab, is that it chooses one way. Well, when there's 5 different ways you can write an answer and they're all correct and one's not more correct than the other, then it's really difficult to know how to enter your answers. So again, in a test situation, if you leave it like this and there's no directions and there's no way that you could have known that you had to factor that out and it marked it wrong, I will look into it. Now I'm going to look really closely at the directions here. Okay, so I'm going to look to see, yeah, did it say factor out, or did it say to do this or that, and you didn't, then I can't give you credit for it. But these two things, to me, I wouldn't know which way to, because it's like 6 of one, half a dozen of the other. All right, they're exactly the same, and I would not consider one to be better than the other. So that's the problem with MyMathLab, is you just really struggle with the final form of the answer. All right, let me just see what's in here. So let's do, okay, so this one's done the same as number 14 and number 16. So this, I'll do 16 since it's harder than 15. And I'm down at the bottom of my screen already. So I'm going to get you a new screen here. It's all about you. What can I do for you? All right. Whoops. Jeez. All right. So what do we have here? We have minus 3 minus root 2 over the square root of 5 plus the square root of 3. And another thing is that really drives me crazy is the final form of the answer will vary with authors. So this author will be doing this type of a problem and want it this way, and then if I switch to my intermediate algebra class, which is a different author, he'll go, no, I want it that way. And so you never know what to do. So ask me, all right? Have me check, because I can look into your test, I can see what you answered, I can see what the correct answer is, and I can look at the problem and I can evaluate it from there. All right, I'm going to put parentheses around these, and I'm going to multiply by my special form of 1, okay, which is the conjugate of that. So again, I'm going to keep these two pieces the same, and I'm going to subtract them instead of adding them, top and bottom. Okay, now I've got a FOIL and a FOIL. I've got a double FOILing problem. All right, so let's do the top first. We've got negative 3 times the square root of 5. Well, there's not much we can do with that. Then we've got negative 3 times a negative root 3. So that'll be a positive 3 root 3. Then I've got a negative root 2 times a root 5, which is a negative root 2 root 5. I'm going to just leave these, I'll simplify in a bit. And lastly, I have a negative times a negative, so that'll be a positive. And I've got root 2 times root 3. Yikes. I don't know how this one's going to turn out. Okay, now I'm going to do the same thing underneath here. I've got root 5 times root 5. I've got a positive times a negative, so this is going to be my negative term, root 5 times root 3. My inside term is a positive root 5 root 3. See how nice those turn out? And then here I've got a positive times a negative, so I'm going to end up with a negative, and I've got root 3 times root 3. Okay? We've got a mess. We've got a heck of a mess here. All right, what can I do? Well, I'm going to combine this and this with my product rules. So let's just do that first of all. Minus 3 root 5 plus 3 root 3 minus root 10, right? I'm going to combine my 2 and my 5 with multiplication plus root 6. I don't think anything in there can be reduced or combined. Yikes. It's going to be interesting to see how it wants the final answer. 2 root 5s is a 5. These are canceling because they're opposite and the same. And 2 root 3s is a 3. So I've got this mess on the top. Ugh. We're going to check this one for sure, see what it wants. So you guys can know. You guys are hopefully are making notes here. Okay. Now I don't know if it wants this split up into 4 different fractions or if it wants it left alone, or I don't know what the heck it wants. So let's just check it. Have you guys been really frustrated with MyMathLab? All right, so this doesn't matter. The order doesn't matter. I know that in MyMathLab that you can put these in any order that you want. They've chosen to put the positive value first. That's this one. That's an etiquette kind of thing. That shouldn't matter again. And then you've got this one. That's this one. So we have a positive and a negative. So I don't know why they put it in that order, but that shouldn't matter. Okay, so this if I put this in like this, I'm sure it'll take it because I've got all the necessary components. It's just in a different order. Multiplication and addition on these usually don't matter. So, on the order. Same thing. Right? I'm going to let you be on that. All right, so now we're going to simplify some of these ugly things. Okay, we don't have a radical in the bottom anymore. But I do have the rule that says this. Okay. Simplify your answer, type an exact answer. Okay, now it doesn't say, again, it doesn't say whether it wants 2 fractions or 1 fraction. So I don't know if it wants this form or that form. I think we'll have to just play around with it and see what it wants. I hope you're not too frustrated with MyMathLab. I know a lot of people get really frustrated with it. Okay, so here's like your A. This is like your A over here, and your B, and your C. So I can split this up. Right? Each piece on the top can get divided by the bottom, which is 10. Now I've got 2 separate fractions that are reducible. Right? I've got 80/10, which is 8, and 20/10, which is 2. Ouch. So this one turned out to be not fractional, so you can't combine, you know, but when we get into these when they're fractional, they stay fractional, then I don't know what it wants. So this one's pretty straightforward. This is what it wants. Now again, in a test situation, I would throw that in your calculator. I would throw that in your calculator and I would check for equivalency. Okay? So here we have 8 roots of 7 minus 2. Good job. All right, so again, you're going to be checking, is there a perfect square underneath here? Can I do anything with my outside pieces? Do I have more than one? Do I have, you know, radical in the denominator, that kind of stuff? So just be careful with that. So that one's the same. I don't think this one is, and I think this is the one that we have to mess with a little bit, so I'll for sure get this one in. And then we're done. But this was almost an hour. Holy moly. Okay, what do we got? We got a mess. I see some stuff that can be reduced up in here though, so maybe I'll do that first. Right? 27 is 9 times 3. And I'm doing groups of 2's because my index is 2, so I can say that's a y squared times a y to the first. So this might take a lot of your radical rules into consideration here. All right, so now I can take the 9 out as a 3, and I can take the y squared out as a y, and what's left is the 3y inside. Don't add those. Okay, so if you can, reduce. Now we're going to split this. So we have 4y over 2y plus 3y times the square root of 3y over 2y. Each piece gets divided by the 2y. And now I'm going to reduce these separately. 4 divided by 2 is 2, and my y's are canceling. So here I only have a 2. Here my y's are canceling, so I have a 3 left over, and that 2 underneath. Now, I'm pretty sure it's not going to want that because I've got two separate fractions. I'm pretty sure it's going to want to combine them into one fraction again. That's my guess. So in order to do that, I need a common denominator, which is 2. I have to turn this into 2's. Well, how many halves is 2? Well, that would be 4 halves, right? Plus 3 roots of 3y over 2. Now I can combine these for one fraction. Yikes, let's see what it wants. Check, 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 come on. That's what it wanted. It wants it underneath one piece. So that's what I was saying about, you know, this is an acceptable answer unless the directions say to, you know, write it as one solid fraction, which it doesn't. So yeah, you're going to have to recombine them into one fraction. All right, well that's it for this section. This was a heavy-duty section. This was a killer, and they're all different, and you just got to be really careful with this kind of stuff. I put a note too that what I'm gonna do for I was just gonna do 9.6 next, but I changed my mind and I'm gonna do 9.6 and 7 together. And what I've done, 9.7 is complex numbers, and I think we need that for college algebra. At least an introduction to that. So what I've done, instead of just doing a lot of problems in 9.6, I've done half the amount in 9.6 and then half the amount in 9.7. So you're going to get the same amount of work. You're just going to get more exposure to what's going on with complex numbers, because I think it's important. So we'll have 2 more shorter lectures to get through, and then we're done. And then we'll test on chapter 9. And then we've just got the 10 and 11 left. So this is going so fast. I can't believe it. Hang in there, and I'll see you for that. Take care.